Hi everyone, I'm Jingqin, a senior research associate at C2SMART University Center at Tongji University. I'm very happy to be here today, and I'm going to talk about traffic safety in the era of connected and autonomous vehicle. Briefly covering USDOT CV pilot and also some new and national efforts in the era of safety regulation. I want to start with some statistics. In 2019, over 36,000 people actually killed in motor vehicle crashes, and 94% of them are actually by human errors, such as distracted drivers. And recently, the adoption of connected and autonomous vehicles are gaining more and more traction, and also introduce new methodology and new technology to alert these drivers and try to minimize the distraction, which align with and also facilitate Vision Zero goal and initiatives. But you may have the question of how much percentage, how much safety benefit can be expected using this technology. And the recent report from National Highway Traffic Safety Administration shows that just by applying connected vehicle technology alone, may prevent 41% to 5% intersection crashes, and ultimately this number can reach to like 80% of all types of crashes per year with all of the CFS. But here comes the second question. How can automated and connected vehicle improve road safety? Well, we know that connected vehicle application exchange information between and among vehicles, which we call it vehicle-to-vehicle interaction, and also with infrastructures and wireless devices to send alert to the drivers. But for automated vehicles, they're able to perform various driving tasks by themselves, such as braking. But to better understand and also better demonstrate those safety benefits of this new technology, I'm pretty sure most of the audience here already know that New York City is actually selected as one of the three connected vehicle pilot deployment by USDOT. And the city installed more than 400, it's specific technology, more than 450 roadside units and over 3,000 vehicles, including taxis, MT buses, a few pickup trucks, and also city-owned vehicles. And importantly, in this pilot, the city is deploying 14 mobility and safety CV applications, including one application that supports people with visual disabilities. And the slides here list all 14 applications, including the vehicle-to-vehicle apps such as blind spot warning. And on the right, you will see the list of vehicle-to-infrastructure apps, including like speed compliance also. And also, we have two additional applications related to pedestrian. One is the pedestrian signalized crossing road warning. Another one is mobile accessible pedestrian system. And here,
in total, the New York City Connected Vehicle Pilot will test 14 safety applications. Let's take a closer look at a few of the connected vehicle safety applications being deployed in New York City. 1 in 4 pedestrian deaths and injuries involve turning vehicles on New York City streets. Connected vehicle technology can provide a life-saving alert to a driver turning at an intersection, warning the driver that a person is in the adjacent crosswalk. In New York City, speeding is a leading cause of traffic fatalities. Connected vehicle technology can warn a speeding driver to slow down, helping the driver avoid a crash, comply with speed limits, and avoid costly speeding fines. Red light running in New York City causes dangerous and sometimes deadly right-angle collisions. The red light detection application can give advance notice to a driver approaching a traffic signal that's about to turn red, helping the driver prepare to stop safely.
As you can see, it is pretty crucial that if we can determine the effectiveness of these safety applications at reducing crashes and how they can actually help in pursuing the general goal, and to show how road drivers will respond to these applications in their vehicles, we'll be able to tell not only estimate the real numbers of how much safety benefits we can actually save from the deployment of connected vehicle technology. Just giving a little bit more detail on one application, which is the mobile pedestrian signal system. So as connected and autonomous vehicle reshape our transport system, they actually offer a critical chance to redress some of the everyday issues, especially on mobility challenged people. So one of these NYCC applications actually intended to assist visually impaired pedestrians in safely crossing streets at signalized intersection. And see the data over here, so the production, they will receive portable devices using smartphone with enhanced GPS signals, what called PID. And these PIDs will receive message broadcast intersection that telling the path about the current status of the signal, as well as the dominate, so that it can verify people and orienting themselves, and also provide viral and vibrating alerts. And we hope this out will actually launch social activities in these. And that's coming back to the evaluation. So the advanced smart cities has also made the field of transportation safety to transition towards new data collection technology. A great example is actually on the right side of the slide, which are the drone-based data collected by our system. And this drone-based data is very cost-effective with outstanding flexibility. And there's other new projects, including leveraging the basic safety messages (BSMs) that detected on the connected vehicles, or using survey safety measure-based simulation assessment. And this can be even brought to the higher level, to develop a psychophysical aspect to help with safety evaluation. So let's start with BSM, and this is actually one of the recent national research efforts to converting the BSM messages into traffic mobility and safety measures. And a basic safety message basically includes attributes that cannot be measured using traditional surveillance technologies such as weight system status or even trigger flags. And also the concept is not new, data is not new. BSM was introduced to the public for a while, but based on vast amounts of literature review that we conducted, we found that current practice show very limited use of certain BSM elements for measure estimation. And there's definitely a need for an open source tool to compute safety measures using the right input data. For example, on the right side, I show you the flowchart of how we actually utilize the BSM data. So from simulated a few vehicle trajectories, we can extract subset of those trajectories based on market reference rate. And using the algorithm such as trajectory converting algorithm, we can turn these information into emulated BS and then process the BSM to estimate traffic measures such as queue length, travel time, or safety measures. In this research effort, there are two common used safety measures such as time to collision or fast acceleration were investigated, and three high priority measures were not selected by a panel of experts nationwide, and the braking, deceleration rate to avoid collision drag, and also time to collision with disturbance TDC. I'm not really going into details about each of these measures. I just want to elaborate here that normal algorithms are actually developed and validated, which overcome the gap of no publisher software for calculating especially the last two measures here, drag and TDCP. And we also designed some additional algorithm testing to help us first to identify the threshold that is the highest correlation coefficient between heart rating, TCV event, and the real crash records. And second, also help us to identify the minimum market penetration rate that's needed to actually obtain those safety measures. And a very important part that I mentioned before is to develop a psychophysical test set because considerable interest in CA knowledge and deployment requires large investment, and this actually demands an effective test set that can create prototyping technologies and also can test, let's say, operational algorithms or policies, and ultimately to turn them into field deployment or field pilot. And under the psychophysical test set framework, both innovators, such as academia, industry, technology providers, and also decision makers are all important elements. And this test set can be used to meet state and cities needs, such as modern effective CAVs on city streets, as well as new technology, new mobility providers. It can be even used for evaluating pandemic impact on new policies. And on the bottom right, this is an example of utilizing large-scale image simulation models to actually help us to test and predict the transit usage before using the pre-COVID model, and also predict what will happen after the reopening of the state. So that as a part of the test bed, we believe a reliable surrogate measure-based image assessment is actually very important, especially for evaluating technical applications, because using traffic simulation models allows us to control the following factors. Only here is we know from the traditional simulation modeling approach, we always calculate the value model of various measures such as traffic count or travel time or travel speed. But here, the goal is really to carry both operational measures together with the safety measures. And to actually calibrate the simulation model, which can mimic the driver behavior in terms of safety, this framework here actually enhance the safety measures part using traffic conflict severity distribution for model calibration and validation. And just very quickly talking about how this framework can be used. So here we use the real-world traffic conflict data extracted on vehicle trajectories that recorded by drone sensor cameras. And multiple key parameters such as like acceleration, map, and can be calibrated. But most importantly, the traffic conflict distribution of different severity level is applied in this framework. And it treats this model calibration process as a multi-objective stochastic optimization problem. And here we apply a method called TSA and the simultaneous integration stochastic approximation to minimize the error between the observed records and simulated outputs to find the optimal tailored model parameters. And finally, we use the 2019 updated FHWA guidelines for performance evaluation, including identifying representative base. So that we're not using average day, we're not using some average numbers, but here using representative days to create variation envelopes. And also criterions, these are actually the formal criterions guided by FHWA for various outlier inlier bounded diamond optical arrows and systematic arrows. And for instance, the results here are for the factor channel model in Blueprint, Blueprint, which is developed as part of the New York City City pilot deployment. And overall, as you can see on the graphic tables, the simulator outputs are invariable agreement with observed link counts, spending amount, and short counts. For the safety part, we use the Cooper-Leaf divergence, which is a measure to measure the goodness of fit of the simulation conflict distribution compared with the boundaries conflict distribution. And low pair divergence values were observed for most locations. That means the observed the simulated conflict distribution are very similar to the observed ones. And it also confirmed that the calibrated parameters can significantly improve the performance of the simulation model, while we consider both the specific measures and operation measures. And lastly, moving forward, although there are a lot of new challenges in the of Tandon and autonomous vehicles, also brings new opportunities such as like shared perception and adoption of connected and cooperative technologies. For example, one good national effort is the USDOT's open source platform Karma, which is designed for research and development of corporate driving automation that focus on autonomous vehicles. There are new standards coming out, such as SAE cooperative practice. I'm pretty sure most of you heard about the automation automation level, but SAE actually didn't come up with this cooperation process as well with the definitions. There's also new technologies, new algorithms such as adaptive connected cruise control that automatically adjust the vehicle speed to maintain stable distance from vehicles. And final level of series such as manipulation cyclicity, social distancing, highly congested and complex urban environment is gaining more and more interest. And with that, I conclude my presentation, but happy to answer any of the questions.